Welcome back everyone for another SVSU Math and Physics Resource Center tutoring video. As always, my name is Brendon and I'm going to be your math tutor. And this video is going to be part 2 of the series testing strategies. Hope you guys enjoy. Alright, so part 2 of the strategies for testing series. I have three series that we're going to be determining the convergence for. So yeah, let's go ahead and just jump right into the first one. So we're going to start with n is equal to 1 ranging to infinity of n cubed e to the negative n squared. Okay, so like as always, the first thing I like to do is I like to quick glance this, right? So what's going to happen as this approaches infinity? So on this one, it's actually kind of hard to tell, right? Because we have this e to the negative n squared term. This is going to go to 0, right? And then this n cubed is going to go to infinity. So this one, let's actually write the n-term test for divergence out, because it's not so readily available just by looking at it. So we're going to take the limit as n approaches infinity of, and I'm going to rewrite this so as n cubed divided by e to the n squared. Okay, so then this gets us, when we plug infinity into our limit, we'll get infinity over infinity. So then that tells us we can use L'Hopital's rule. So then we're going to take the derivative of the top and derivative of the bottom. So this is going to be the limit as n approaches infinity of, looks like 3n squared divided by 2n e to the n squared. Okay, and so then that's going to end up being the limit as n approaches infinity. Looks like we get some n's to cancel out here, so it's going to be a 3n over 2e to the n squared. Okay, so now that we have that, we can try plugging in our limit again, or our infinity again, but it looks like we're still going to get infinity over infinity. Okay, so then that tells us we can use L'Hopital's rule again. So we'll do the limit as n approaches infinity. So derivative of the top this time is just going to be 3 over, looks like 4n e to the n squared. Okay, and then this is definitely going to be 0, right? Because our denominator is going to go to infinity while our numerator is staying at 3. Okay, so then that tells us we did all that work for the n-term test for divergence to be inconclusive, right? So then that tells us we have to try another series test. So let's see, what other series test do we want to try to do? So typically I would go to I would try to do a direct comparison test, right? But in this case, I'm not seeing a function that's going to be easy to directly compare this to. So we typically, when we try to use direct comparison, we'll try to use something like a p-series or a geometric series that we easily know if it converges or diverges based off of those two types of series. But I'm not really seeing anything in here that's going to make it easy to compare. So I'm thinking direct comparison and limit comparison for this one are kind of last resorts. Okay, and so then let's go to the next one. So let's think about the integral test. Do we want to do the integral test with this series? Let's see. So would this be easy to integrate? We could make our u substitution this here. We could maybe try integration by parts. I'm thinking that the integral test is taking the integral of this might be pretty difficult. So then I think that one's going to also be a last resort. So let's think about the next test. What are our next ones? We can use the ratio test. Okay, let's try to do the ratio test. So if that's our a of n, so then our a of n plus 1 term is going to be n plus 1 cubed e to the negative n plus 1 squared. Okay, and so then let's go ahead and simplify this. So this is going to be, I'm going to move this piece to the denominator. So this is going to be n plus 1 cubed divided by e to the n plus 1 squared. And then let's go ahead and simplify this again. And I'm going to go over, because we're going to do our ratio test underneath this. So this is going to be, if we expand the numerator, we're going to end up with n cubed plus 3n squared plus 3n plus 1 divided by, and if we expand that, we're going to get e to the n squared plus 2n plus 1. Okay, so then this is going to be our a of n plus 1 term. So now let's go ahead and do the ratio test. So we're going to take the limit as n approaches infinity of the absolute value of a of n plus 1, so that's this term that we just wrote out, and so it's going to be n cubed plus 3n squared plus 3n plus 1 divided by e to the n squared plus 2n plus 1. And then, so the ratio test is a of n plus 1 divided by a of n. So we're just going to do a of n plus 1 multiplied by the reciprocal of a of n, right? So our reciprocal of a of n is going to be e to the n squared divided by, let's see, this is going to be n cubed. Okay. So now that we have that, we can actually break this term up into each individual piece, right? So this is going to be the limit as n approaches infinity of the absolute value of n cubed plus 3n squared plus 3n plus 1 divided by, so now I'm going to break this up in each individual piece. So it's going to be e to the n squared times e to the 2n times e to the first power multiplied by e to the n squared divided by n cubed. Okay, so it looks like we're going to end up getting our e's to the n squareds to cancel, which is nice. And then we'll be left with, let me write it out. So we'll have the limit as n approaches infinity of the absolute value of, let's see, we're going to have n cubed plus 3n squared plus 3n plus 1 divided by, looks like n cubed multiplied by e to the 2n times e to the first. Okay, so now that we have that, how are we going to solve this limit? So I see our highest power is n to the third on top and n to the third on bottom, but we also have this extra e to the 2n in here. So what I'm going to try to do is I'm going to multiply by 1 over n cubed to try to get rid of that. Divided by 1 over n cubed. Okay, so now that we did that, let's go ahead and distribute those through and simplify. So we're going to have the limit as n approaches infinity of the absolute value of 1 plus, it looks like it's going to be 3 divided by, let's see, that's going to be n plus 3 divided by n squared plus 1 divided by n cubed divided by, so on the denominator our n cubed is going to cancel out. So it's going to be e to the 2n times e to the first. Okay, so when we take this limit, what's going to happen is these pieces are going to go to 0, going to go to 0, and going to go to 0. And then it looks like we're just going to be left with 1 over infinity, which is equal to 0, which is less than 1. Okay, so now that we have that, or we've done the limit of a of n plus 1 divided by a of n, and we got it to be equal to 0, through the ratio test, that tells us that our series converges. And not only converges, it converges absolutely. Okay, so that's kind of how we went through the process of, we went through the n-term test for divergence, got it to be equal to 0, which is inconclusive. And then we ended up doing the ratio test, and we got the ratio test to work out. Okay, so let's go ahead and go to the next one. Okay, so just like the last one, on this one, let's go ahead and start out with the n-term test for divergence again. So we're going to do the limit as n approaches infinity of, let's see, n cubed 1 plus e to the n divided by 1 plus n cubed. Okay, so to do this limit, what we need to do is we are going to expand this term, and then we're going to divide by, or multiply top and bottom by 1 over n cubed. So this is going to be the limit as n approaches infinity. So I'm just going to expand the denominator. So n cubed times 1 plus e to the n divided by, let's see, this is going to be n cubed plus 3n squared plus 3n plus 1. Okay, so we're going to multiply this both on top and bottom by 1 divided by n cubed and 1 divided by n cubed. Okay, so on the numerator, our n cubed is going to cancel. And on the denominator, we're going to end up with, I'll go ahead and write it out. So the limit as n approaches infinity. It looks like on the numerator, we're just left with 1 plus e to the n divided by 1 plus 3 divided by n plus 3 divided by n squared plus 1 divided by n cubed. Okay, so if we plug in our infinity to this, it looks like we're going to get, all of these terms are going to go to 0. That's going to go to 0, that's going to go to 0, and that's going to go to 0. So it looks like we're just going to end up with an infinity over 1, which is just equal to infinity. So in this one, the nth term test for divergence did work out. So we went through and we got this series to diverge because it's not equal to 0 through the nth term test. So diverges. And that's one of the reasons I always try to check the nth term test for divergence first, right? So then we don't have to start out with doing another test that might take a little bit longer, because the nth term test for divergence is typically pretty quick. Okay, let's go ahead and take a look at this last one. I'm actually going to contradict myself a little bit. So typically I always start out with doing the nth term test for divergence. But if I'm looking at this one, taking the limit of this as n approaches infinity is going to be pretty tricky with this 2 to the 3n in the denominator, and this alternating term, which we can make to be like a negative 1 to the power of n, right? So I'm already seeing that this is alternating, right, because of this negative being raised to a power of n, right? So as n goes from an even number to an odd number, this is going to change from a negative number to a positive number. So that tells me that this series is alternating. So I'm going to go ahead and jump right into the alternating series test. Okay, so I'm going to write out our a of n is equal to negative 3 to the n plus 1 divided by 2 to the 3n. Okay, and I'm going to simplify this a little bit. So in my simplifying steps, I'm going to break this negative 3 up into our alternating term that we typically see, which would be a negative 1 to the power of some function of n. So then this is going to be negative or positive 3 to the n plus 1 times negative 1 to the n plus 1. We can just imagine there being a negative 1 on the inside and a 3 being multiplied together, and then the exponent's going to go to both of them. And then divided by, and then on the denominator, I'm going to simplify this and make this 8 to the n. So 2 to the third power is 8, and then to the power of n. Okay, and then there's one more maybe 2 more steps I'm going to do. So the first thing I'm gonna do is break up my 3. So I'm going to have 3 times 3 to the n times my alternating term, which is negative 1 to the n plus 1, and then divided by 8 to the n. Okay, and then so one last simplifying step just to make the writing it down for the alternating series. That's a little easier. As I'm going to make this a 3 times a negative 1 to the n plus 1, and then this is going to be 3 over 8 to the n. Okay, and so now the alternating series test says that if we have our series, what we can do is we can take out the alternating term, this negative 1 to the n plus 1. We'll take that out and we'll call that our b of n. So I'm going to write that down. So b of n is going to be equal to 3 times 3 over 8 to the n. Okay, and so there's 2 stipulations for the alternating series test. If b of n is decreasing and the limit as n approaches infinity of b of n is equal to 0, then that tells us that the series converges. Okay, so we're just going to go ahead and check those 2. So decreasing, how do we know if this is decreasing? Well, this constant's not going to really affect if we're increasing or decreasing, but this term is, right? So what's going to happen is as n increases, this is like 3 to the power of n divided by 8 to the power of n. Our denominator is going to get bigger faster than our numerator. So if our denominator is getting bigger, that tells us our expression is getting smaller. So that tells us that it's decreasing. Another couple ways you could check this is by graphing this function, and then you'll see that it's decreasing. Or you can take the derivative of this and see what the sign is on your derivative. Okay, but we know that it's decreasing, so I'm going to write out decreasing, check. So that's the first part, and then the next part is the limit as n approaches infinity of b of n. Okay, so let's go ahead and solve this limit. So it's going to be the limit as n approaches infinity of 3 times 3 over 8 to the n. Okay, so with our limit rules, what I'm going to do is I'm going to pull this 3 out. So it's going to be 3 times the limit as n approaches infinity of just 3 over 8 to the n. Okay, and so let's see what can we do here. So I think I want to get this this n out of the exponent, right? So I'm going to do my e to the ln kind of trick that we have. So this is going to be 3 times e to the ln of the limit as n approaches infinity of 3 over 8 to the n. Okay, and so then we can move the natural log inside of our limit. So it looks like we're going to end up with 3 times e to the limit as n approaches infinity of the ln of 3 over 8 to the n. Okay, and then using our natural log rules, we can take the n and move it out front. So it's going to be 3 times e to the limit as n approaches infinity of n times the natural log of 3 over 8. Okay, so now if I plug in my infinity here, this is just a constant, but the important thing to know is that this is a negative constant, right? So when ln is less than, or when our argument of our natural log function is less than 1, our function is negative, okay? And then when we plug our infinity to n, we're going to get infinity times a negative number, which is going to be like a negative infinity, right? So this is going to be 3e to the negative infinity, which is equal to 3 over e to the infinity, which e to the infinity in the denominator is going to go towards infinity, which is just going to be equal to 0. Okay, so then through the alternating series test, we know that our b of n is decreasing, and the limit as n approaches infinity is 0, so then that tells us that our series converges. Okay, so we went through 3 examples, 5 if you count the last video, of just random series, and then the ways that I like to work them out and go through the process of determining what test to use for what series. So I hope you guys enjoyed the videos.